So good morning one and all. So let us start today's class. So in the last class we have started with some basics of linear algebra. Okay. So let us go through these basics of the course linear algebra, which you might have studied in your E2 or E1. So what is a basis vector? Basically it is a fundamental vector using which we can define any other vector. So what is the first and foremost condition to be satisfied is linearly independent. Okay. Basis means a set of vector belong to Rn. What are they? Suppose V1, V2, so on, Vn are a set of vectors which belong to Rn. Okay. So if I say belong to Rn means they are the vectors of n-dimensional whose elements are real. That's the meaning of belonging to Rn. If I say belong to R2, which means these are two-dimensional vectors belong to real values. Suppose 2, pi. They are real values. Okay. All the values of this vector has to be real, and furthermore they has to be two-dimensional. If it is R2, it should be two-dimensional. If it is R3, it should be three-dimensional, something like this. 1, 2, 3. Okay. Now, so a set of vector belong to Rn are said to be basis if they are linearly independent. What do you mean by linearly independent? I told you in the last class also. If you take the linear combination of these vectors, suppose C1 V1 plus C2 V2, so on, Cn Vn should be equal to 0. If and only if the only solution for this is what? So this is 0 if and only if only one condition. What is that? C1 equal to C2 equal to Cn equal to 0. Okay. So if it is so, then we say that the set of vectors v1, v2, vn are called linearly independent. Okay. So the linear combination should be 0 only if the scalars are 0. Otherwise, you can also write c1 v1 plus c2 v2 plus so on cn vn is not equal to 0 except c1 c2 equal to 0 or cn, so on. Okay, so the definition is very simple. This is the definition. This equation is true if and only if the only solution for the above equation is all the scalars are 0. Okay, then they are said to be a linearly independent. Otherwise, they are linearly dependent. Okay. Now, if you have a set of vectors which are linearly independent, then every vector belong to Rn can be expressed as a linear combination of these vectors. Okay. Now, basically, the basis vector means a fundamental vector using which you can represent any vector as a linear combination of these vectors. Okay. Now, so let us take simple example. So let us take space R2. Space R2 means two-dimensional space, something like this. X, Y. So basis vectors are fundamental vectors. Basis vectors need to be linearly independent. Okay, remember this. Now, what do you say? Now let me take these two vectors 1, 0, 0, 1. What are they? The vector 1, 0 and this is vector 0, 1. What are they basically? They are the unit vectors in the direction of the coordinate axis. Okay, this is vector x, this is vector y, isn't it? So what you can say about these two vectors? So I am assuming a space of R2, two-dimensional space. I am assuming two vectors as 1, 0, ys 0, 1. Are they independent? Yes. Why? Because c1x plus c2y equal to 0. If and only if c1 equal to c2 equal to 0. So for this equation, the only solution is this. Do you agree or not? That's why these two vectors are linearly independent, because you cannot find any other c1 c2 values other than 0, so that this equation is satisfied. Okay. Now, so here now these two happen to be linearly independent. Now they can be called as a basis. They can be called as a basis vectors. Why? Because if you take any vector which belongs to R2, let us take AB. How to represent AB? Now this can be the vector, any vector, random vector can be written as linear combination of basis functions or basis vector. What are the basis vector? 1, 0, 0, 1. This is 1, 0 plus 0, 1. What are the scalars now? Scalars has to be A, here it is B. Okay. Now, what is this? What is AB now? Now we can able to represent any vector. See, remember, any vector AB as AB. AB is belong to what? R2, because it is a two-dimensional vector that can be written as some scalar A into X plus B into Y, some other scalar B into Y. Okay. What are X and Y? So we can able to write any random vector which is belong to R2 as a linear combination of two basis functions X, Y. A and B are scalars. Okay. So you can take for example, so 5, 3, otherwise 2, 7. How to write this? As a 2 into 1, 0, 1, 0 plus 7 into 0, 1. So in this way you can write any vector which is belong to R2 as a linear combination of these two basis functions with the different scaling factors or coefficients. Okay. So what is this? 2 into 2 plus 0, 2. Next 7. Okay. This is how we write. Now these are called basis vectors. Yeah. So here this basis vector need not be unique. Okay. So don't think that always we take basis vector only 1, 0, 1, 0, 0, 1. No. You can take any vectors which are linearly independent. Okay. So there is no rule that you should always take these as a unit vectors or basis vector, or also called fundamental units. Okay. You can choose any random vectors, but those vectors has to be linearly independent. Then we can use them as a basis vector to represent any other vector which belongs to that particular space. For example, I am taking 2, 3, 5, 7 as basis vectors. You can take, suppose 2, 3, 5, 7. Okay. So these are basic vectors. Let us take X, Y. These are basis vectors X, Y. So then how to write AB? Any vector AB can be represented as so C1 or X1. You can take X1 into what is this vector? 2 3 5 7. 2 3 plus x2 another scalar 5 7. Okay, then what we can do? So a equal to, from this what is a equal to? 2x1 plus 5x2. 2x1 plus 5x2. b equal to 3x1 plus 7x2. 3x1 plus 7x2. If you know a and b, solve for x1 x2. These are scalars, no? In this way you can choose any vectors as basis vector, provided what a condition? They should be linearly independent. All the basis vector has to be linearly independent. What is linear independency? The linear combination is 0 if and only if the scalars are 0. Okay. So in this way, there is no compulsory that you should always choose basis vectors as unit vectors along the coordinate axis. There is no such rule. You can take any vector as a basis vector provided they satisfy certain conditions. Okay, right. Now these are the basis vector we have taken in the starting. Those are unit vectors in the direction of the coordinate axis x comma y. This is a space belong to R square or R2. Suppose here you have any vector, something is like this. This can be any vector in the space. What is space? Two-dimensional space. This vector can be represented as linear combination of these two basis vectors x and y. That is simple logic. Okay. Now, so if you move further, I am taking u1, u2, un as a basis vector which belong to n-dimensional space. Okay. Now, any vector z as a linear combination of these vectors. Obviously, what do you do? I am taking u1, u2, un belong to Rn. They are the basis vectors of what dimension? N-dimensional. Which means, what is u1? You write u1 is a vector of n dimensionals. Elements are, let us take u11, u1n. What is u2? Another basis vector. u21, u22, u2n. Like this we have a n basis vector of dimensional n. This is n cross 1. Okay. Now what they are saying is, yeah. So all these are, how are they? Linearly independent. All these u vectors are linearly independent. They has to be, because if they are basis vector, they has to be linearly independent. Now then what we can do? So we have a vector z which belongs to Rn. Now this z can be represented as a linear combination of what? Alpha 1 u1 plus alpha 2 u2 plus so on plus alpha n un. Okay. So any vector z which belongs to Rn can be represented as linear combination of basis vectors. Okay. Now what are they? They are simply scalars. Alpha 1, alpha 2 are scalars. Okay. Like this. So if you take only two-dimensional, u1, u2 are basis vectors. Any vector z can be represented as a linear combination of these two basis vectors. Let me like this: alpha 1 u1 plus alpha 2 u2. If it is two-dimensional. Okay. Yeah. So, but this is z. What is this? u1. What is this? u2. What is this? un. So if you combine them properly, you get this matrix form. Okay, this vector z, this vector u, this matrix u, this vector alpha. What is vector z contains? Z1, Z2, Zn. What is the matrix u contains? So what are these columns? Each column is a basis vector. This is u1, this is u2, this is un. What is the vector alpha? Is a vector containing the all scalars or multiplication coefficients. Okay, so finally what you can write? So z equal to what? U into alpha. Okay, in this case what you can write here? So z equal to vector z equal to u. What is the matrix u? It contains columns as basis vectors. What are the bases here? u1, u2. Okay, u1, u2. Sorry, u1, u2. Next, alpha 1, alpha 2. What is z? They contains z1, z2. z1, z2 equal to u1, u2 into alpha 1, alpha 2. So remember this simply. Okay. So remember they are basic vectors. u1, u2 are basis vectors. You must try and find out what are the vectors. u1 means u11, u12. u2 means u21, u22. Like this. Is it okay? So the columns of the matrix, this matrix are basis vectors. u1, u2 are vectors. Don't simply consider them as elements. Okay. Now let us see if we go with one more special condition, that is orthonormal. You know already orthonormal. Orthonormal means what? Orthogonal plus unit energy. We have studied these things in our ADC course. If these two are combined, it is called orthonormal. Okay. So unit energy means normalization simply. It indicates normalization. What is normalization means? Divide the quantity with itself, its magnitude. Okay, suppose let us take a simple example. We have vectors, set of vectors v1, v2, so on, vk. When can you say they are orthogonal? Their dot product is 0. Vi dot vj equal to 0 if I is not equal to j. Okay, so this is a condition for perpendicular or orthogonal. So each and every vector is perpendicular to other vectors in the set. We have set of k vectors. When can you say they are orthogonal to each other? The dot product of any two different vectors has to be 0. Then we say that they are perpendicular or they are orthogonal to each other. Okay. Now how to make them orthonormal? What do you do? So suppose they are orthogonal already. v1, v2, so on, vk, a set of vectors which are orthogonal already. How to make them orthonormal? Just divide with its magnitude. Or this is called norm. Okay. Now they are orthogonal as well as they are simply having unit vectors. v1, v2 becomes unit vectors. I mean the magnitude is 1. or the energy is unity. So they are orthonormal. Which means if you have a set of orthogonal vectors, you can make them orthonormal just by dividing each and every vector with its magnitude. Okay, that's why orthonormal, orthogonal or can be used interchangeably. So sometimes if I say orthogonal, by default they are orthonormal. Okay, I don't specifically always say that they are orthonormal. If I say they are orthogonal, by default they are orthonormal. Okay, even though they are not orthonormal, we can make them orthonormal just by dividing each and every vector with its magnitude. It is not a big deal. Okay, so I hope you are okay with this, right? What a condition. Now let us see if we have a orthonormal basis. What a condition? This is the condition. Obviously, so yeah. Suppose if you multiply, if you take the dot product of signals itself, okay, orthonormal means suppose Vi dot of Vj has to be 0 if I is not equal to j. If I equal to j, Vi dot Vi, which means mod Vi square has to be 1. Correct? If these two are satisfied, simply they are orthonormal. So they are orthogonal and they are having unit energy. Okay, so if a set of vectors satisfy these two conditions, they are said to be orthonormal. Now let us go back to our case. We have a Z. This is definition. Just now we have seen. Okay. One more thing I told you. So the dot product also same as what? I told you in the starting itself. Suppose Vi transpose Vj is same as dot product Vi dot Vj. This is has to be notified. Is it okay? So here I am using this transposition formula instead of dot product. Okay, the first one itself says Ui dot Uj. The second one indicates Ui dot Ui. The dot product of same vectors. Otherwise, a dot product of signal with itself. Okay, now let us proceed further. This is Z. Now what I am doing is I am multiplying with U1 transpose on both sides of this equation. What happens? This is what you get. But what is U1 transpose U1? 1. This is 1. What is U1 transpose U2 from this equation? This is 0. What is U1 transpose U1? Also 0. You are left with only alpha 1. Okay. Similarly, what is alpha 2? Z transpose U2. Otherwise, you can also write reverse. Okay. From this, I can say that so I have written Z equal to, let me write equal here, Z equal to, what I have written, Z equal to alpha 1 U1 plus so on alpha n Un, isn't it? Now, so what is U1 transpose Z equal to alpha 1? Obviously, how to get alpha 2? U2 transpose Z equal to alpha 2, just like alpha 1. Or you can also write Z transpose U2 also gives you alpha 2. It is also valid. Both are valid. Okay. Now, so in this way, what is the advantage? You can easily calculate these coefficients. What are they? Alpha 1, alpha 2, so on, alpha n. How? What is the logic? Using dot product between z and ui. Correct? What is this actually? u1 dot z. What is this? u2 dot z. So if you simply by taking dot product, we can able to identify or we can able to find all the scalars or all the coefficients of the z, like alpha 1, alpha 2, alpha n. Isn't it? Okay. Okay. Now that's why we need to have a orthogonal basis functions, because they are the most convenient basis functions. Okay, here let me tell you one thing. I told you the basis functions has to be what? If you remember in the starting itself, I told you they has to be linearly independent. But what I am saying is, for convenience, they has to be, the basis function has to be orthonormal. Okay, I think I am contradicting my statements itself. Okay, what do you mean by this is, here I have written orthogonal, here I am writing orthonormal. I told you both are same, both are interchangeable. Why? Because if you have a set of orthogonal vectors, you can make them orthonormal just by dividing every vector with its magnitude. This is not a big deal. Okay, now here for convenience, our basis function has to be orthonormal. What a convenience? What a convenience? You can easily find out alphas just by taking dot product between ui and z. By just taking dot product, you can find out these coefficients. That is the convenience. But it is possible if and only if all the basis vectors are orthonormal. But I told you, basis has to be linear independent, Li. Okay, so here the logic is very simple. So the logic is, so if they are orthonormal, if any vectors are orthonormal, they are by default linearly independent. Okay, if I say they are orthonormal, they has to be linearly independent. Okay, so there is no problem now. If I say the basis vectors are orthonormal, it is for our convenience. But if they are orthonormal, always they will be linearly independent. But the converse may not be true. Would the converse? If they are Li, they need not be orthonormal. If they are orthonormal, they are linearly independent. No problem. Okay. So remember that from now onwards, our basis functions are orthonormal. Okay. I hope we have used orthonormal basis functions in our ADC course also. Right. That is about basis functions. Now, so that is about basis function. Now let us come to our linear algebra, complete linear algebra. So our eigenvectors can form a basis. Okay, what is eigenvectors? All those things we have started with eigenvectors only. What is that? Suppose we have a matrix A. It has some eigenvalues, lambda 1, lambda 2, so on, lambda r. And correspondingly, it will have eigenvectors. These are eigenvalues, eigenvectors. Let us take E1, E2, otherwise x1, x2 let us take. x1 is eigenvector corresponding to eigenvalue lambda 1, x2 is eigenvector corresponding to eigenvalue lambda 2, this is xr. Okay. Now what is one more thing? Ax equal to lambda x. Suppose if lambda 1 is the eigenvalue, x1 is the corresponding eigenvector. Okay, this is the simple logic. What is x1? Eigenvector corresponding to eigenvalue lambda 1. Okay. Now, so what I am saying is these eigenvectors can now act as a basis vectors. Okay. So before proceeding further, what I told you about basis vectors. If they has to be Li for sure. Okay. But if they are orthonormal, it is more convenient. Okay. They has to be Li for sure, compulsory. If they are orthonormal, it is for convenience. Furthermore, if they are orthonormal, by default they are linear independent. Okay, remember this. So, basis function need not be orthonormal. It is only for our convenience. But they has to be compulsory linearly independent. Okay. Now, okay. So now we will use our eigenvectors as a basis vectors, which has to be compulsorily linearly independent. Okay. Now we have two theorems. What theorem 1 says? The eigenvectors of a matrix A which belongs to Rn having distinct eigenvalues are linearly independent. Okay. What theorem 2 says? The eigenvectors of a square symmetric matrix are orthogonal. Okay. So remember this. What they are saying is, if a matrix A belongs to Rn in cross n. Theorem 1 says, if a matrix A we have, so it has distinct eigenvalues. Let us take lambda 1, lambda 2, so on, lambda k. K distinct eigenvalues. And for each and every eigenvalue, we have a eigenvectors. K eigenvectors. Each eigenvector for each eigenvalue. So they are distinct. If it is so, what they are saying? The eigenvalues are linearly independent. These eigenvectors are Li. If any set of vectors are Li, they can be used as a what? Basis. Okay. Okay. So these are the two theorems which are very important. So if A is a square matrix, remember it is a square matrix. Why? Because it is n by n matrix. So if A is a square matrix and it will have some distinct eigenvalues and the corresponding eigenvectors are Li. If they are Li, they can be used as a basis vectors. That is one thing. What is theorem 2 says? If it is a symmetric, square as well as symmetric. What is symmetric? You know already. A transpose equal to A. If it is a square symmetric, what happens? So they are not Li, not only Li, they are orthogonal. Orthogonal means by default you can make them orthonormal. So now in this case also they can be used as a basis. Okay. Now if it is square symmetric, we have a convenience. Why? Because the eigenvectors are orthogonal. They can be used as a basis, and if they are orthogonal, by default orthonormal, you can easily identify these scalars. Okay, that is the logic. Theorem 1, theorem 2 are very important. Right. Now so we will briefly go with this eigenvalue decomposition. I'll start now itself. Yeah, so u1 u2 un be the eigenvectors of a matrix A. Let lambda 1 lambda 2 lambda n be the corresponding eigenvalues. Okay, so they did not mention it is a square symmetric or not. They simply said it is a square matrix. That's it. Okay, now so let me write here a matrix A as a square matrix as lambda 1 lambda 2 so on lambda n eigenvalues and corresponding eigenvectors are x1 x2 so on xn. These are eigenvectors. Now we are defining a matrix U whose columns are, okay, I told you write it differently. They are calling this as U1, U2. Okay, no problem. Let me write this. The corresponding eigenvectors are U1, U2, so on, Un. Okay, these are eigenvectors. Okay, now so let us define a matrix U whose columns are what? Eigenvectors. Matrix U as a columns, each and every column is an eigenvector. U1 is a vector. See, U1 is a vector, is not a value or element. What is U1? U11, U12, so on U1n. Okay. Next U2. U2 is another eigenvector. U21, U22, U2n. So and so. Okay. So U1, U2 are not the elements, they are the vectors of n-dimensional. And the matrix U, its columns are eigenvectors. Okay. Now let us define AU. A into U, matrix multiplication. You take A inside. Okay. And furthermore here, what I can say is Ax equal to lambda x, you know. Okay. X are eigenvectors, lambda is eigenvalue. So AU1 equal to lambda 1 U1. Correct? So U1 is an eigenvector corresponding to eigenvalue lambda 1. Okay. So here AU1 is what now? Lambda 1 U1. Lambda 1 U1. Next lambda 2 U2. Lambda n UN. Now further you can write, see U1, U2 are simply eigenvectors. They are not simply elements of a matrix. That's why I indicated with the arrows, up arrow, down arrow. Which means the elements in the above U or below U. I mean below U1, above U1. Now this is a matrix multiplication. I hope you know this, how to write this. Okay. Now what is this? Matrix U whose columns are eigenvectors. And this is lambda, capital lambda. This is lambda. What is lambda? It is a diagonal matrix whose elements are eigenvalues of a matrix C. So AU equal to U lambda. Lambda is something called capital lambda. Okay. What is this lambda? It is a diagonal matrix with the diagonal elements as what? Eigenvectors. sorry, eigenvalues, I'm sorry. Okay. Now, so if U inverse exists, what is the, okay, let me write. When do we get inverse? When can a matrix have inverse? If its column space is, otherwise, if its columns are linearly independent. If a matrix has a columns which are Li, then for that matrix there exists a inverse. Okay. Now is it so? Yes. Why? Because the columns of the matrix U are what? Eigenvectors. Eigenvectors of a square matrix are Li. Li means linearly independent. Obviously, U inverse exists. Okay, why? Because A has n distinct eigenvalues, n linearly independent eigenvectors. Obviously, the eigenvectors of the columns of the matrix U and the columns are linearly independent. That's why its inverse exists. Okay. Now, if it is so, what you can write? AU equal to U lambda. Is it so? If inverse exists, let us take pre-multiply with U inverse here also. Okay, let me write here. If inverse exists, AU equal to U lambda. If inverse exists, let us pre-multiply with U inverse. What will happen? This is I. Sorry. This is I. I into lambda. Okay. What will happen here? U inverse AU equal to lambda. Okay. That is pre-multiplication. So you can also multiply post. What will happen? Okay, let me write here. Case 2. AU equal to U lambda. Post multiplication with U inverse. So this is I. I means identity matrix. A into I is A. A equal to U lambda U inverse. Now we have two possibilities. Now this is called eigenvalue decomposition, EVD. This is called diagonalization. Okay. So that is about two things: eigenvalue decomposition and diagonalization. Okay. Anyway, we stop here. Thank you.